Good day to everyone. We are Group 2 and going to present to you one of our fluid mechanics experiments, the stability of the body. This experiment was conducted on 17 April 2023, monitored by Dr. Afiq. The group member consists of me, Chua Jia-en, Chia Hui-Sing, Shani, Kyle, and Sulaiman. The objective of this experiment is to comprehend the principle of stability in a floating object influenced by the metacentric state, and to determine the height of the metacenter using a tilting method. A vertical downward force of gravity, which is equivalent to the weight of the body, W, acting at the center of gravity, G, and an upward vertical buoyancy force, Fb, which is equal to the weight of the water displaced by the immersed body, which passes through the centroid of the displaced volume of water, that is the center of buoyancy. Now, for a floating body to be in equilibrium, the buoyancy force should be equal to the weight of the body. Also, the center of gravity and the center of buoyancy should lie on the same vertical line called the center line BG. If a body undergoes an angular displacement, let's say in the rightward direction, then we can see the volume displaced is larger in the right side, so the center of buoyancy shifts towards to the right from B to B prime. Then a couple is formed which tries to rotate the body. The point of intersection of the vertical line through the new center of buoyancy, B prime, and the center line BG is termed as the metacenter of body, and the distance by which the metacenter lies above the center of gravity of a floating body is known as the metacentric height, GM, which is given by depending on the location of metacenter. A floating body possesses three types of equilibrium, which are stable, unstable, and neutral equilibrium. When M is above G, then a restoring couple is formed by the buoyancy force and the weight of the body, which tends to turn the body to its original position, so the body is said to be in stable equilibrium. When M is below G, then an overturning couple is formed by the buoyancy force and the weight of the body, which tends to sink the body from its original position, so the body is said to be in unstable equilibrium. When M coincides with G, then in this case, the line of action of buoyancy force and the weight of the body are collinear and pass through the same point. Due to this, the body neither returns to its original position nor increases its displacement further, so the body is said to be in neutral equilibrium. In the experiment, the stability of a ponton is determined with the CG at different heights. The equilibrium condition of a floating body can be determined experimentally as shown in the formula below. We will explain it in more details in the results and discussion section.
The first step is to measure the length and width of the pontoon, and the total mass of pontoon with vertical wake and the mass of horizontal wake are both taken using an electronic balance. And the total mass of pontoon with The next step is remove the horizontal wake, and the height of vertical wake of the pontoon was fixed and measured. Then place the pontoon on the pontoon stabilizer and make sure the shorter side is at the bottom. Next, the pontoon is adjusted accordingly until it balances on the pontoon stabilizer, and the length of the center of gravity was measured from the base of the pontoon to the middle of the beam. The horizontal wake was fixed and the position of thread is set at 0 mm. Then the pontoon was placed in the tank and the depth of the pontoon submerged in the water was measured. This is an example picture for submerged depth measurement. Next, the horizontal wake was moved to 10 mm to the right, and the angle of tilt of thread is recorded when the string is stopped swinging. The previous step was repeated with an increment of 10 nm until the plumb bob, which is hanging on the thread, touched the side of the pontoon, and repeat the same step on the left side. The height of the vertical weight was adjusted, and then the previous procedure was repeated. The whole experiments were conducted 3 times in total with different vertical height, bottom, middle, and top.
The first error present in this experiment, which has influenced the experimental results, is that the plumb bob which is hanging on the thread does not touch the side of the pontoon. This is because the horizontal weight cannot move sideways any further. This is illustrated in the pictures shown. Next, another error present is called the parallax error. This happens when the observant's or spectator's eye is not perpendicular to the level of the scale, causing inaccuracies when taking measurements. Lastly, it is found that the pontoon apparatus was possibly damaged or faulty since there was a small hole present at the corner, causing water to leak into the cavity of the pontoon, possibly altering or manipulating the accuracy of the experimental results.
Next, I will discuss about the results and calculation. The result we obtained is mass of horizontal weight is 0.3636 kg. Total mass of pontoon with vertical weight is 1.1693 kg. Width of pontoon is 200 mm and length of pontoon is 348 mm. And this is our result table. Then we need to calculate the values of GM for test 1 top, test 2 middle, and test 3 bottom. And we need to calculate for movement to the right and movement to the left. And we use the formula GM equal to mass of horizontal weight multiplied with distance x and divided by total mass of pontoon with vertical weight tan theta. And we obtain the result as shown here. Next, for discussion part 1, plot the graph of GM versus theta and determine the value of GM from the plotted graph when theta is equal to 0. First, the graph shown below is GM top for the movement to the right, and GM obtained is 38.303 millimeters. And for the second graph is GM middle for movement to the right, and we get the value of GM is 43.759 millimeters. For the third graph is GM bottom for movement to the right, and we obtain the value for GM is 89.959 millimeters. And the fourth graph is GM top for movement to the left, and the value of GM is 45.201 millimeters. Then the fifth graph is GM middle for movement to the left, and GM obtained is 149.04 millimeters. And the last graph is GM bottom for movement to the left, and the GM is equal to 74.624 millimeters. For discussion part 2, calculate the value of GM for each test using an area of second moment. Compare and discuss the obtained value with the value of GM from part 1. Formula for GM theoretical is equal to I over V minus Y plus D over 2, which is I is equal to length of pontoon multiplied with width of pontoon divided by 12, and volume of water displaced is equal to total mass of pontoon with vertical weight divided by density. And the volume of water displaced that we obtain is 1169300 millimeters cubed. And we use the formula to calculate for test 1, test 2, and test 3. And this is the summary table to compare the GM from line equation and GM from area of second moment. And the formula to calculate the percentage error is GM theoretical minus GM experimental divided by GM theoretical and multiplied with 100%. From the percentage error, we can conclude that there are some errors that occur during the experiment. For example, the pontoon pole is not connected tightly to the pontoon, hence the pole can be moved easily and causes zero error to occur, although the position of the thread is adjusted to 0 at the beginning of the experiment. Thus, it is important to ensure the pole is connected tightly to the pontoon. Next, parallel error that occur when taking the reading of scale. Always ensure that our eyes are perpendicular to the reading of scale and may repeat the experiment to obtain more accurate results. Moreover, when the surface of the water is always in motion due to external force like air movement, which in turn result in higher difficulty to obtain accurate reading on the scale since the thread swings. Third, it is advised to conduct the experiment in a computer space. The values of GM from calculation and graph are different because the theoretical value depends only the dimension and weight of the pontoon and the distance between water surface to base of the pontoon. But the experimental value depends on the angle of the plumb pole. Therefore, the theoretical values are more accurate than the experimental value.
I will be discussing on the reliance of metacenter on the position of center of gravity in terms of stability of a floating body. Metacenter. Metacenter is a point where the line of action of buoyant force intersects an imaginary vertical line through the center of gravity of a floating body. Metacentric height, denoted as GM, is the distance between the center of gravity and metacenter. Larger metacentric height provides greater initial stability against overturning moment. There are two conditions. Metacenter above the center of gravity creates a stable and equilibrium position. The second condition, metacenter below the center of gravity makes the body unstable, not in equilibrium. Further, I will be discussing on the variation in angle of tilt on the position of metacenter. Angle of tilt causes a change in position of metacenter due to change in the center of buoyant and center of gravity, as described by the equation. Equation helps calculate the position change based on weight distribution and buoyancy force. Higher tilt angle leads to a reduced stability. Stability determined by the metacenter height, which is the distance from the center of gravity. Stable condition, metacenter above the center of gravity and positive metacentric height ensures stability. After having conducted the experiment, we can finally conclude that the experiment showed a discrepancy between theoretical and experimental value of metacentric height due to measurement errors and environmental factors. Metacenter position plays a crucial role in determining stability of floating bodies. Tilt angle affects the position of metacenter, and the stability depends on the metacentric height. Metacenter above the center of gravity indicates stability, while below indicates instability. Lower tilt angle results in increased stability. Height adjustment and submersion aid in determining stability.